14.1 is on life tables. In a life table, we can describe a cohort or a generation as a life table that is a record of the actual observed mortality experience for a particular group, where the data is collected over periods spanning decades of time. So they are not practical and not commonly used. A period, which is current, that's a life table that describes mortality and longevity data for a hypothetical synthetic cohort with the data computed with this assumption. The conditions affecting mortality in a particular basis year remain the same throughout the lives of everyone in the hypothetical cohort. The components of a period life table, such as the one I have open over here on the right, the first column on here is the age interval, with some overlap with the upper boundary and lower boundary of the next age range, meaning this is 0 to 1 and the next is 1 to 2. The second column is the probability of dying during that interval. That's the probabilities of dying during the associated age interval. This reflects the death rates for the various age groups that were observed in 2010. The third column is the number surviving. This is the number of people alive at the beginning of the age interval. The first row lists the hypothetical population size to be 100,000 people, right here. To find the next row, we take the number surviving, and multiply it by the probability of dying. So 100,000 times 0.006123. And then subtract from that number, from that same value. So we will subtract whatever that number there becomes. What was that? 612 about. So we subtract 612 to get the next value of 99,388, and then it goes so on and so forth from there. Column number 4 is the number of deaths during the interval. So that takes the number of people who died during the age interval. We multiply the number of people alive at the beginning of the age interval, column 3, and multiply that by the probability of dying during the age interval, column 2. And that number just goes in that column. Likewise, for column 5, this is the person years lived. This is the total time in years lived during the age interval by those who are alive at the beginning of the age interval, which is why these have such long numbers. Well, big numbers, I should say. Column 6 is the total person years lived. This lists the total number of years lived by those present at the beginning of the age interval and all of the following age intervals as well, which is why that, as you can see, these numbers do decrease as we go down the table. The last column, column 7, is the expected remaining lifetime. This lists the expected remaining lifetime in years measured from the beginning of the age interval. We divide the total person years, column 6, by the number of people who are present at the beginning of the age interval, column 3, to get these values. And we can make an abridged life. Well, this is an example of a complete table. It has a separate row of data for each year. An abridged life table is that the age intervals have been combined, so the age intervals are longer than 1 year, such as 5 or 10 years. This table here is an example with 5. An abridged life table is to be constructed using age intervals of 5 years. Using table 14.1, we want to find the expected remaining lifetime for someone reaching the 25th birthday. So, because of this, for the 25th birthday, that being down over here, we see this expected amount is 54.7. 54.7 being that expected remaining lifetime. For the abridged table, the expected remaining lifetime for someone reaching the 25th birthday, we'll have that same value of 54.7 years. So that for that 25 to 30 column, we'll have that 54.7 as the expected remaining lifetime. Using 14.1 again, we want to find the probability of a person dying between the ages of 15 and 20. So, between 15 and 20, at their 15th birthday, we could see that there were 99,154 people alive. And we could also see that for the 20th birthday, we could see that the number surviving was 98,910. So this is for the 15th. The 20th was the 98,910. So for the probability of survive between 15 and 20, we are going to take 98,910 and divide that by 99,154. When you do so, you get an answer of about 0.9975539. So this is for surviving. Since we want the probability of dying, we're going to take 1 minus the probability of surviving that we just calculated. So 1 minus 0.997539. This will give us a value of about 0.002461, which, as you can see, is a very small number. But anywho, example number 3. Let us assume that there are 3,932,181 births in the United States this year, based on data from the U.S. National Center for Health Statistics. If the age for receiving full Social Security payments is 67, how many of those born this year are expected to be alive on their 67th birthday? So, from this table, among these 100,000 people that were born, if we go down to the 67, down here, we expect that 82,098 of them will survive to the 67th birthday. Which means the probability of someone surviving from birth to the 67th birthday to survive to 67, we would take that 82,098 divided by 100,000. This gives us a value of 0.82098. And if each of the 3,932,181 newborn people has that same probability of 0.82098 of surviving, we would take the 3,932,181 181 and multiply by 0.82098. Tossing that into a calculator, we get an answer of about 3,228,242. And that's the expected to survive to their 67th birthday, which, as you can imagine, is something that's important to, let's say, for example, the Social Security program or health insurance and the like. And then finally, example number 4. In the chapter problem, we know that for one region there were 50,000 people who there were 5,000 people who reached their 16th birthday. If 25 of them died before their 17th birthday, do we have sufficient evidence to conclude that the number of deaths is significantly high? So, for this, for the age interval of 16 to 17, according to this table, we had the probability here of dying of 0.000412. But this refers to originally the 25 deaths among 5,000 people during the age interval. For this region, the proportion of actual deaths, we would take p hat to be 25 out of 5,000. This would give us a value of 0.005, less than 1%, as you can imagine. We could proceed to test this claim for this region, with the deaths from a population with a death rate greater than that value from the life table of 0.000412. We could test this by using a hypothesis test of p equal to 0.000412, and the alternative, well, p is greater than 0.000412. If we go about actually computing that, we would obtain our z-test statistic here of 15.99, and the p-value that we get for this would be 0. So because of this, we are rejecting the null hypothesis. So let me write this out down here. So we are rejecting the null hypothesis. So we have sufficient evidence to support the claim that the proportion of deaths is significantly greater than the proportion that is usually expected for this age interval. Let me know if you have any questions or concerns. Thank you.